Yeah, keep it shared.
Yeah.
We're live.
Hi, everybody. Welcome to the afternoon session of QMAT on the second day. Today's chair would be, the chair for this session would be Subhra Bhattacharjee from ICTS. Just a few announcements. The long talks are 25 minutes plus 5 minutes question and answer. Short talks are 13 minutes plus 2 minutes question and answer. We would keep the questions for the end of the talks. If you have a very urgent question, type it in the chat and we can take it up after the talk has ended. And if there is a long discussion that breaks up, you can use one of the breakout rooms which we have created so that you can keep the discussion going while the talks go here uninterrupted. With this, I will hand it over to Shubhro. Shubhro, you are the chair of the session now.
Thank you, Rasdeep. So we have 4 talks in the session, starting with Sumiran Pujari from IIT Bombay, and who would be talking about resummation-based quantum Monte Carlo for quantum paramagnetic phases. So Sumiran, I'll give you a reminder at 22 minutes, and then you would try to summarize in the next 3 minutes so that we can have 5 minutes for questions.
Yeah.
Okay. So Sumiran, you can start.
Okay. Thanks, Shubhro, for this introduction. And also, I would like to start by thanking the organizers for giving me this opportunity to present some recent work. So as you can see, the title of the talk is Resummation-based quantum Monte Carlo, so the talk is going to be about an algorithmic technique to simulate quantum paramagnetic phases. So these would be something like valence bond solids or something where even at low temperatures, the system does not magnetize. So this work was done in collaboration with Nisheeta Desai. It started when she was sort of in transition from University of Kentucky, where she did her PhD, to TIFR, where she's a postdoc now. And she'll also be giving a talk later in this session on some other work. And the work has been got started actually in the thick of the pandemic. So it was productive in some sense, and it's published, and you can see the paper for more details. So let me give a brief outline. So I will start by a basic introduction of what is the quantum Monte Carlo framework that I will be talking to you about. This is called stochastic series expansion technique, SSE for short. And once I give this introduction, which will essentially set the stage for what is the resummation-based update that we are proposing. After explaining the basic idea of this update, I'll explain some performance-related results about this update. And after that, I'll discuss some more physical result, which is connection of SUN magnets to quantum diamond models. And after covering this topic, I will quickly maybe sketch how to extend this technique to higher symmetric or higher spin representations of SU2 or SUN. And in the first part, majority of the talk, I'll focus on the sort of fundamental representation. So before I get to the actual algorithmic part, the main part of the talk, let me give a brief idea of where quantum Monte Carlo and our contribution situates itself in the study of quantum matter. So as goes without saying, algorithms are indispensable for studying quantum matter or any situation where the complexity gets high very quickly. So strongly correlated setting algorithms are indispensable. So some well-known techniques are exact diagonalization, which are generally limited to small clusters of sites. Then there is the well-known class of algorithm based on DMRG, pioneered by Stephen White and its extensions like matrix product states and tensor networks. The main class of another big class is the Monte Carlo based methods. This is where quantum Monte Carlo techniques there are many kinds of quantum Monte Carlo techniques. So one of the old techniques is path integral based Monte Carlo for interacting fermions in the continuum, started by Sepperli, and then there are other successor algorithms. There are also determinantal or what is called auxiliary quantum Monte Carlo for interacting fermions on the lattice, so started by Hirsch and then continued by many people. Then there are some diagrammatic based quantum Monte Carlo started by Swistinov and Prokofiev, and then where our contribution fits in is what is called generally worldwide or SSE based quantum Monte Carlo techniques for interacting spins on a lattice. So this was originally pioneered by Sandbeck, and many people have contributed along the way. Then there are variational Monte Carlo techniques, one when we have some good ansatz for the system. And then there are other classes of techniques for time evolving some quantum Hamiltonian, which is another sort of broad area in this area. So, so a general comment is that computation is of course very important as a tool to understand quantum matter, but we also now find that computation often aids understanding, and sometimes it is understanding. So it is with that I will launch into our algorithm. So the stochastic series expansion technique is the backdrop are magnetic insulators, so Heisenberg models where the charge fluctuations have frozen out or are not important to the physics, and it is really the spin degrees of freedom which are playing the role. So the say the prototypical model is the Heisenberg model, equation 1. And the SSE technique generally pertains to the equilibrium properties of any system, of your model of interest. So the general idea of any quantum Monte Carlo technique is you take the partition function, the quantum partition function, and you try to map it to an effectively classical partition function. So you map it to a new space where the configurations are effectively classical with given weight functions. And then if you can arrange for these weight functions to be positive, then you can apply probabilistic Monte Carlo techniques to the problem. So one reference point could be the D to D plus 1 quantum classical mapping that we learn in textbooks. So you can think of equation 2 in that light. And part of the algorithm design lies in doing this mapping. And then we have a viable quantum Monte Carlo technique. And for SSE, we start with a high temperature series expansion of the quantum partition function. So this is the high temperature expansion, the trace over e to the minus beta h. You expand this, it's a high temperature series, the standard exponential expansion. And what one has to really deal with, algorithmically speaking, is how to compute these traces. And so originally, people like Hanscom tried to compute it by hand, so to speak, but then Sandvik and others gave the idea that one could actually sample these traces in a Monte Carlo sense and set up a computational technique. So the main challenge is that this trace of h power n, we have these n factors of h acting on in some basis, let's say the SZ basis. So whenever h acts on an SZ basis states, it actually creates a superposition of many states. And so the algorithm has to deal with this messiness. And so the idea is to convert the matrix elements into some simple roots. So the standard SSE goes as follows. So we take our Heisenberg Hamiltonian or bond Hamiltonian on a single bond, and it has a diagonal piece and an off-diagonal piece. The diagonal piece is SZ, off-diagonal is S plus S minus plus summation conjugate. And we can arrange such that the rule becomes on any bond, if I have a parallel spin configuration, then it always gets annihilated by either of the diagonal or off-diagonal operators. Whereas and then for the non-zero matrix elements, the diagonal piece, of course, keeps anti-parallel spins aligned, and it gives this minus j by 2 matrix element, whereas the off-diagonal piece flips anti-parallel spins and gives a plus j by 2 matrix element. With these simple rules, now I can draw pictures to illustrate these rules. So this is a typical quantum Monte Carlo configuration after doing this kind of a high temperature series mapping. So as you can see, so this red and white dots indicate the spin state. And you can see that anytime the operator is present, it is always between anti-parallel spins. There is always a red and a white side for any of the operators. And there is never an operator between, say, white and white and white and white. So this is not allowed. This is due to the fact that parallel spins get annihilated. And you can only insert or put operators once you get into this anti-parallel configurations. And also you have to respect the trace condition. So the starting state and the final state has to be the same. So given these constraints, we arrive at what is called the operator string representations, the same partition function is essentially represented by a string of operators or matrix elements at different.
Sorry, Sumiran.
Yeah.
What are the black and the white lines?
So the black and white lines are, so the white line is a diagonal operator. So the spin configuration on both sides are the same. So this is the diagonal piece. And the black line is the off diagonal operator. So the spin has flipped around by the action of the operator. I hope that's clear.
Yeah, sure.
Yeah. So then the representation just is a string of such matrix elements, a sequence of either no flip or spin flips, anti-parallel spin flips, such that I start at in some given state alpha and end up in that alpha. And so the B is an index for where these matrix element, which bond they are getting contributed from. The mu is whether they are diagonal or off diagonal. And we only need to include non-zero matrix elements because then only otherwise the weight function is just zero. So the configuration, the effectively classical configuration is defined by how many such matrix elements are there, n, small n, the sequence of these matrix elements, so they can be in different sequences, so that is indicated by Sn, and what is the starting state, if you wish, alpha. And through the matrix element calculations, we find that each diagonal piece contributes beta j by 2, each off-diagonal piece contributes minus beta j by 2, and they are equal in magnitude due to SU2 symmetry of the Hamiltonian. And so to ensure that the weight of each configuration is greater than 0, you actually need even number of off-diagonal contributions, off-diagonal operator contributions, which is actually, turns out, ensured on bipartite lattices. Whereas when you have some frustrated lattices, say triangular lattice or some other sources of frustration, this is generally not ensured. This is called the sign problem. So some final details, equipped with this effectively classical configuration and a positive weight function, I can perform standard Monte Carlo techniques. You need, in standard SSE, you use two kinds of Monte Carlo updates. One is called the diagonal update, where you insert or remove diagonal operators at different locations in your operator string. This also updates the small n, which has to be updated. But a really powerful update is what is called the off-diagonal or loop update, where you actually, the diagram that we draw can be decomposed into these loops. For example, this red one is a loop. And on this loop, you can just change all the spins. You can flip all the spins. So the red goes to white, white goes to red. That is what has happened from left to right. In the process, n does not change, but you interchange diagonal and off-diagonal operators. So that's how you update off-diagonal operators. By virtue of this being a non-local update, this actually is a very powerful update in the Monte Carlo sense. And then various quantum observables can also be measured via appropriate estimators. So a simple estimator for energy is just you count the number of these non-zero matrix elements in your operator string. Of course, computationally, you just compute the change in that and you sum them. But you can measure quantum observables is the main point. And there are otherwise no approximations except for statistical or sampling errors. So now this is the basic setup of standard SSE, and now I'll start going towards the resummation-based update. So for this, it is useful to see the sign-free property of bipartite lattices for Heisenberg models through a sublattice unitary transformation. So on one of the sublattice, on any bipartite lattice, you can do a sublattice unitary such that the matrix element now takes this form. Instead of anti-parallel spins, as mentioned before, it's as if it is operating only on parallel spins. But now what happens is both diagonal and off-diagonal operators, say alpha equals beta or alpha not equals beta, contribute same sign, beta j by 2, a positive quantity to the WC. And so therefore, in this sublattice rotated basis, WC is manifestly a positive quantity. And when we do this little trick, we re-represent the operator string as a closely packed colored loop representation. So the same diagram that we drew earlier can be now drawn in this way. And now we can easily generalize the SU2 to any SUN. It essentially consists in allowing these loops that were being non-locally updated in standard SSE to have n colors instead of 2 colors earlier. So this representation actually allows for a resummation step. Essentially what you do is you resum over these colors. So each loop can have n colors, say 2 for SU2, and you just sum it over and you get a factor of n to the n loops, however many loops are in the this new representation. And again, in the process, you have diagonal operators where say alpha alpha goes to alpha alpha, or off diagonal operators where you are going from alpha alpha to some beta beta, and you are resumming over all that. So now when you resum, you don't draw it in this colored way. There is no distinction between diagonal and off diagonal. And now in this uncolored representation, I will perform my Monte Carlo. And this n of SUN, symmetry of the model, is now like a loop fugacity parameter. So whenever n becomes large, this typical configurations will have more loops. And we perform Monte Carlo in this uncolored configuration space, and the technical details are in the paper. The main computation that you have to do is the change in number of loops due to the dependence of the WC, the weight on n loops, the number of loops, and that has similar complexity as the old off-diagonal update of standard SSC. This RSSC, actually, now I'll discuss the performance of this algorithm. Standard SSC has a well-known bottleneck, if you wish, as n becomes larger. Essentially, the diagonal update, which removes or inserts diagonal operators, becomes inefficient. This is basically because if you look at equation 4, as n becomes large, there are only n diagonal operators from each bond, but there are order n square of diagonal operators. So what happens is typical configurations have way more off-diagonal operators than diagonal operators. So therefore, standard SSC diagonal update does not really update the configuration that efficiently. But we expect the resummed version of SSC to not suffer from this because it has no distinction between diagonal and off-diagonal operators anymore. It can remove or insert operators anywhere that you want, of course, probabilistically. And we do find, so this plot summarizes, this is the autocorrelation for energy estimator. It becomes very efficient as n becomes large, the autocorrelation drops very fast. And this is a proof that the algorithm works. So some more performance results. So this is one well-known physics result that as n increases for quantum antiferromagnets, non-magnetic phases are generally stabilized at low temperatures. So for example, valence bond solids and so on. And so we expect this resummed SSC to have better autocorrelation or performance properties with respect to those observables that will generally be of interest. So these are the quantum paramagnetic phases alluded to in the title slide. So one well-used operator is the VBS order parameter. So this is the detail. But what the plots show is that the autocorrelation time of while you're measuring the VBS order parameter, actually the resummed SSC always outperforms the standard SSC for large n. For smaller n, it does not outperform, but for large n, resummed SSC generally does better and should be the algorithm of choice if you're interested in some large and non-magnetic phases. Another performance result, so the VBS histograms actually have proved quite useful in the literature. So these VBS order parameters that we defined, you can measure the order parameter value, but you can also make a histogram of them as you are doing your Monte Carlo simulation. And so those histograms have given a lot of insight into, say, the theory of deconfined critical transition, where the emergence of U1 symmetry at the transition point was shown through the use of these histograms. And what we show basically is that the resummed SSC does a much better sampling of this VBS histogram space than standard SSC as n becomes large, precisely because it does not get stuck. The diagonal, there is no way for it to get stuck because I can insert and remove operator anywhere. And the limitation is this resummation step works naturally only when you have SUN symmetry. But if many models of interest do have that symmetry, in which case this generally outperforms. The fact that this is a fair comparison, we have explained it in the paper, so you can look at the details to make sure that this is a fair comparison. And really the underlying reason for the increased performance of this resummed SSC is the following. It's not really related to the fact that when n gets larger, somehow the algorithm is getting better, even though that is a consequence. It is really the fact that in this uncolored loop language, magnetic phases which are generally stabilized at small n, are long loop phases. So typical configurations have actually few or many long loops in your configurations, Whereas the quantum paramagnetic phases like VBS, for example, are generally dominated by short loops in your typical configurations. And the point is the change in n loops computation, that RSSE is a key computation, time-taking computation of your RSSE, becomes very efficient in short loop phases. So that is the underlying reason for the increased performance of this algorithm. And so even for quantum paramagnetic phases at small n, this should be the algorithm of choice. Even though standard SSE performs pretty well even then, but say if you're interested in some subtle things this might give you better statistics. Okay, so now I come to some physics results in some sense. So this is where the connection to quantum dimer model aspect of our work. So it is known that SUN magnets, as n becomes very large, more precisely in the n going to infinity limit, leads to what are called quantum dimer models. So this is an example of a quantum dimer model on a square lattice. So the quantum dimer model, the Hilbert space is a dimer configuration on your square lattice, and you have a hopping term where two parallel dimers can be flipped, and you might have an interaction term. So for SUN magnets, this is the dominant term. And doing quantum Monte Carlo for this Hamiltonian was not really possible, like finite temperature simulations, but only very recently there have been some SSE-based algorithms for such. The technical challenge was how to handle the constraint, the dimer constraint. And the result of this new development in algorithm space is what is called the mixed phase histogram results due to this new algorithm. So the point is there are many possibilities. So the mixed phase refers to whether you have columnar order or plaquette order of the quantum dimer model, or perhaps a mixture of the two. And what this result, if you're interested in the details, you can look at this PRB 2021. They claim that for the relevant regime, it's actually a mixture. So this right bottom figure shows what a mixed phase histogram is. So it's a mixture of the columnar and plaquette order. But a natural question for us was to ask, what does the resummed SSE, or in general SSE, find as n grows larger? Because this algorithm is more efficient, you would naturally use this to answer that question. What we found is that there are only U1 symmetric histograms. So bottom, just a second. Look at the bottom two panels to the left. These are representative of the low temperature limit. For large n, you find that the VBS order extrapolates to a finite quantity. However, the VBS order histogram doesn't show any mixed phase character. It is rather U1 symmetric. So this was a physics result that we found in our paper. And furthermore, we can actually see the emergence of the QDN constraint Hilbert space as n grows. And this requires, Shupro, how much time do I have?
You have like 4 minutes, a little less than 4 minutes,
okay,
3.5 minutes.
Okay. So yeah, thanks. So this really requires interpreting what are the quantum states in this uncolored resummed SSE. So recall that in standard SSE, they were actually well-defined SZ spin configurations. So if you look at the left side of this figure, say at each side at any imaginary time slice, there is a well-defined spin, say blue color, which might be up spin, and maybe this down spin or something. For SUN, there are n colors. However, to see the QDM Hilbert space, one has to interpret what is the quantum state at any imaginary time slice in this uncolored representation. And it turns out, so this I'll skip the details, it's given in the paper, they turn out to be essentially VBS states, or rather overlaps of two VBS states. And so for experts, this is really connected to the VBS basis quantum Monte Carlo of Sandvik and Sandvik-Everts and the transposition graphs of VBS states. And but at finite temperature, it turns out that the Hilbert space cannot be captured just by pure VBS states, but you can also have monomer defects. So for example, if you look at this particular loop, because it is periodic in time, when you try to interpret it, what is happening at some time slice, you find that there are monomers. So I'll skip the details. But I can make precise the emergence of the quantum Dimer-Hilbert space or not. And the main point is that for SUN antiferromagnets always have too many monomers for typical configurations at even at low temperatures. So this is the thing which shows that. So this FD is the fraction of quantum states from typical configurations, which are valid constrained Dimer-Hilbert states. You see that for very large n, so n equals 50, it goes very close to 1 as temperature goes down. But even for very like fairly large, but not too like say n equals 15, already I have 0.8 is the fraction of quantum states which are actually valid Dimer QDM Hilbert space states. There are too many. 0.2 fraction have actually monomers. So the main point is that SUN magnets are quite far away, practically speaking, from the neighborhood of QDM Hilbert space. And to really see the proper QDM physics, say if the mixed phase histogram result is right, there is some debate on that in the literature. We really need to go to absurdly large n or really low t to see that. And so this is a physical, I believe this is a physical relevant point for real VBS ordered magnets, that they are.
Sumiran, you have a minute to wrap up.
Yeah.
And then after that question.
Sure. I'll wrap up. So for real materials with VBS ordered magnets, I believe the U1 kind of fluctuations will play a role in the observables. So the final few slides were about the extension to higher representation, higher spin or symmetric representation. Let me just skip this because it will be impossible to cover this, except to mention that it can be done. And also the spin stiffness rho is measurable in RSSE. And so the details are in the paper. And so with this, I'll come to the conclusion side. The details are in this published paper. There are some interesting connections to closely packed classical loop gases in one higher dimensions. There's a series of papers written by Nehum et al. And our algorithm also connects the deconfined critical models like JQ models to some deconfined critical transitions in this closely packed classical loop gases. We have some comments on this in the paper. Some possible future avenues is this might give us some new estimators, maybe to probe some low energy emergent gauge dynamics, but we don't know. There are some precise questions posed by Kedar Kamble, for instance, where maybe there is some opportunity. And this algorithm might be useful for some other algorithm. For example, you can have a look at Dimitrios algorithm to measure entanglement entropy in magnets. So this might be very useful there. So with that, I'll thank you for your attention. I'll acknowledge my funding sources, IIT and DST, and I acknowledge heartily my discussions with Fabian and Kedar. So with that, I'll take questions.
Thank you, Sumiran. So now we can have some questions, and just raise your hand, and then I'll read out the names. First of all, Arnob Shane, you can ask your question.
Yeah. So hi, Sumiran. So
Hi.
So I was just wondering, so in this way of doing things, using these uncolored loops, I think you even mentioned it in your conclusions. Is there a way of writing an improved estimator so that you can sort of measure the low energy spectrum in the valence bond side? Because it turns out that in the usual SSC way of doing it, you can do this improved estimator stuff for the magnetic side, but it's not so easy to do on the other side. So
yeah, improved estimator, we didn't think about it, but the estimator, we used the same estimator as standard SSE. The algorithm itself was much more improved. So that's where you really gained. If there is some improved estimator for VBS, I can't think of on the spot, but maybe I can mention that the spin stiffness rho has an improved estimator, it turns out, in this resum way of thinking. So, but the algorithm is not as efficient, it turns out, in the magnetic phase. So even with the improved estimator, you don't gain much. But for VBS, it's really a non-issue because the algorithm just is very good.
I see. Okay. But even then, I mean, if you sort of try to measure some correlation in the imaginary time, if you have an improved estimator, then it really helps your statistics a lot.
Yeah.
But
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 there
maybe
might be some opportunities there.
Yeah, but maybe we can talk offline about
Sure.
Yeah, I think you can also use one of the breakout rooms. So the next question is by Debashish Banerjee. You can unmute yourself and ask the question.
Hi, Sumiran. Thanks for the nice talk. Devashish here. So, a very nice question. So, if you take n tending to infinity in your SUN antiferromagnet, right? So, which value of V in the quantum dynamic model are you supposed to land up?
As far as my understanding goes, it should be V equals 0. Because, that's why I showed this histogram. So, my understanding is, as n tends to infinity, any dimer at n equals infinity, any dimer configuration is a ground state. And then 1 by n correction at lowest order will give these quantum fluctuations, these dimer split flips.
So just to repeat this question, if you wanted to scan the phase diagram for non-zero values of V, you presumably have to add another term to the SUN antiferromagnet.
Yes. Something like a Q term possibly or something.
Exactly. But that would make them even more complicated, isn't that right?
Yeah, that will be more complicated, but yes, it will be more complicated. But the point we are making is that this is not the way to access that physics, because you always will have monomers. So you can't really, you see what I mean?
Yeah, I think I do, but let's talk offline.
Okay, sure.
Thank you.
Yeah.
Any more questions? Sumiran, can I ask a quick question myself?
Yes, please.
I couldn't quite catch. Do you know what the monomers are doing?
No, except for the fact that they bring in enough quantum fluctuations to make the histogram U1 symmetric, but that is just describing the result. Maybe there is some theory opportunity there, like thinking from the point of view of the RG flows in presence of monomers.
Right.
QDM fixed point, but I don't know. I don't have any real insights.
Maybe we can talk about that.
Sure.
Okay, good. Sure. Yeah. Okay, let's thank Sumiran for the nice talk once more, and we will have the next talk. Is Sthitadhi around? So would you share your screen?
Yeah, I'll just share my screen.
Yeah.
It's okay, right? The screen share.
Yes, this is visible. So, okay, so we'll move on to the next talk by Sthitadhi Roy from University of Oxford, and he would be talking about measurement-induced entanglement phase transitions in random quantum circuits. And Sthitadhi, your talk is for 25 minutes, but I'll give you a warning at 22. Okay?
Sure.
Okay, good.
Okay, thanks, Shubhra, for the introduction, and thanks to the organizers for putting this together and inviting me to talk about some work. I'm going to talk about measurement-induced entanglement phase transitions in random quantum circuits. There's a lot of words in the title, but I'll try to sort of explain the things slowly. And this work was done with Adam Nahum, who has now moved on to ENS Paris, Brian Skinner from Ohio State, and Jonathan Ruman from Bar-Ilan. And this is the reference which has all the details. All right, so I mean, before I sort of get into the talk, let me just say that, how do we sort of think about quantum entanglement in a very naive sense, and why do we care about it? So the point is that you can think of quantum entanglement as, very naively as a web of non-local correlations throughout the system, and sort of characterizes all sorts of things like whether a state is separable and so on and so forth. Now, the reason we care about quantum entanglement is because, or at least in a modern context, is because entanglement can be used to distinguish different phases of quantum matter, so which goes beyond the conventional paradigm of classifying phases via local order parameters and so on. But more sort of in a further, more recent context, and how I came to sort of be interested in this problem is from a slightly quantum information view of this entire subject, which is quantum entanglement actually encodes that how strongly is the information shared between different parts of the system. And then you can ask sort of related questions that how robustly is information encoded in a state, and can it be destroyed by local perturbations and errors and so on? Because at the end of the day, the kind of questions we want to ask is how easy or how difficult it is to prepare or manipulate a particular quantum state and retrieve quantum information from it. And it turns out that quantum entanglement is a measure which tells you a lot about these things. Now, in particular, I'll be interested about the dynamics of quantum entanglement. So I won't be interested in entanglement in some eigenstates of a system and so on. I'd rather be interested in the dynamics. And sort of the philosophical reason behind this is that, operationally, you can think of quantum mechanics being a theory of unitary dynamics and non-unitary measurements. So what we would like to do is, manipulate quantum states and store or retrieve information using them in real time. And this is not just some, theorist's dream. Indeed, this is what the modern sort of quantum processors, such as the Google's Sycamore processor, is doing. And here's a picture from the paper that they wrote in 2019, where they sort of claimed quantum supremacy. I'm not going to go into that, but the essential idea is that you have a bunch of qubits which have been put on some architecture, and you can make the qubits talk to each other. So you can think of, in this picture, the vertical axis as space. You have all the qubits here, and this horizontal axis over here is time. And what you're doing is you're making the qubits talk to each other, interact with each other via a set of unitary gates. And once you have run your circuit, this is called a quantum circuit. When you have run your circuit for a certain number of cycles or certain time, you then go and measure the state of the system and try to extract information from this particular system. So obviously, if you have a setting like this, it's a sort of a departure from the conventional way in which we are used to thinking about condensed matter systems, namely Hamiltonians and their eigenstates. But this is rather a sort of dynamical quantum system with unitaries and measurements, and we would like to understand the dynamics of quantum entanglement in these systems. So a simplified view of the picture that I had on the previous slide is this. And in the rest of the talk, I'm going to think of space horizontally and time vertically. So I have a bunch of spins or qubits. There's a set of unitaries which act on it. And we normally know that if I run this unitaries for a long enough time, then basically two parts of my system is going to get strongly entangled with each other. You can measure that entanglement via the Feynman entropy of entanglement or some Renyi entropy. That detail is not important here. But what we typically understand is that this entanglement grows linearly with time and then eventually saturates to a volume law. Now you can ask the question that once I intersperse this unitary dynamics with measurements, which I'm denoting here by these red dots and the broken lines, for example, it could be a projective measurement, what does it do? Now, of course, the intuition is that, well, measurements basically collapse your wave function locally, and that degree of freedom basically gets disentangled from the rest of the system. So the entanglement dynamics is going to be slower. Now, the crucial understanding here comes from the fact that if you sort of have the rate of measurements as some sort of an axis in your, or some sort of a parameter in your dynamical rule, then there is a critical measurement rate. And what I mean by a critical measurement rate is that there is a genuine phase transition which separates two phases. So in one phase, when the measurement rate is below this critical rate, the long time state, of course, it's a dynamical state. The state is not a steady state, but the entanglement in that state is a volume, law. Whereas basically, if your measurement rate exceeds this critical measurement rate, then you eventually, your long time state, although again, it's a dynamical state, it actually has area law. And this has implications for what kind of states and dynamics you can actually prepare efficiently on a classical computer, and for what kind of things you need to go to a quantum computer and so on. But we are not, for the rest of this talk, I'm going to take a very statmechy view of the whole problem and not really worry about that aspect. In particular, I want to understand this phase transition over here, which basically comes about because of a competition between the entangling unitary dynamics and the disentangling projective measurements. Okay, so what are the questions here? So of course, because we have a new sort of phase transition, we would like to understand its critical properties. Where is the critical point and what's the scaling near it? Now, if you think a bit about this problem, you'll immediately realize that there's a question here, which is that is this phase transition a quantum phase transition or a classical phase transition? I'll elaborate on this. And then, of course, you can ask questions about connections to other kinds of entanglement transitions. For example, many of us know that the many-body localization transition can be understood as an entanglement phase transition and so on. And So these are the kinds of sort of questions that I'd like to have answers to. Now, of course, this is a very, although it's a random circuit, the unitaries are random and the measurements bring in their own randomness and the measurements can be placed randomly. This is a fairly structured model. It's a 1+1D local quantum circuit. So what we sort of thought was, okay, let's try to make life simpler and hope that we can get exactly solvable models by getting rid of spatial structure and deal with all-to-all connected two local circuits. So what do I mean by this is that basically any two qubit in the model can talk to any other qubit, but all these interactions happen only pairwise. For example, one way of drawing it is that you basically take the world lines of the spins and move them around so that you can make any qubit talk to any other. Or another way of visualizing it is that you put the qubits on a ring and then sort of place our unitaries randomly between them. And of course, these red dots denote the measurements. But this brings in a complication, which is once you have this all-to-all connected model of qubits, you don't have a distinction between volume law and area law because everything is connected to everything. So there's no way you can sort of bipartition the system in any reasonable way. So what we need to do is we need to motivate a new observable for the phase transition. So let me do that. So the way we think about this is we consider this non-unitary operator, which is made up of these unitaries and these measurements. Let's call this non-unitary operator as V. It's a bona fide time evolution operator. And you can ask that how much quantum information actually flows through the circuit in time. And that's simply quantified by the operator entanglement entropy of V. Now, mathematically, you can write it in the following way. So you have a time-dependent operator. You can singular value decompose it and normalize the singular values appropriately. And then just like you would compute things for a density or a reduced density matrix, you basically compute the nth Renyi operator entanglement entropy in this fashion. Now, let me try to give you two extreme limits to convince you that this is actually a good measure. So suppose...
may I ask a question right now?
Sure, yeah, right.
So in your previous picture, when you were doing the measurements, you just had this one red dot. So
yeah.
Now it seems to be disconnected upon measurement. Is that significant?
Yeah, so basically what actually happened was I moved to a projective measurement. Okay. So when I do a projective measurement, you naturally project the spin onto one of its states, and then that naturally disentangles it from the rest of the system. So you can think that its world line starts again. So the line is actually broken.
You're forcibly projecting the spin to any of the up or the down spin?
Depending on the Born rule probabilities.
Okay, okay. And
so,
what about?
Sorry, what about?
These two disconnected dots?
Yeah, so I mean, okay, this one single red dot is essentially the same as these two dots. I mean, one was made for the paper, the other was made for the so,
yeah. I see. Thank you so much. Thank you.
Okay. All right. So let me try to sort of convince you that this operator entanglement entropy is a good measure. So suppose I take one limit where there are no measurements. So then this V is purely unitary. So modulo some normalization, the singular values are all going to be unity, or modulo some normalization and phase, which doesn't matter. So naturally, the operator entanglement entropy is going to be n log 2. N is the number of qubits, log 2 because I'm dealing with qubits and not qubits. So this is the maximal and the extensive operator entanglement entropy in the limit of no measurements. But now suppose I have a circuit where I have no unitaries and I just have measurements. So in that case, you can easily see that basically this singular value decomposition has only one singular value, which is 1, and everything else is 0. And that basically corresponds to, the JT state corresponds to the state after the final set of measurements. And the J0 state corresponds to the state just before the initial round of measurements. So in this case, because there's only one singular value, which is 1, your operator entanglement entropy is actually 0. So clearly, this seems to work in the two distinct limits. And the question is that whether, I can use this as an order parameter for the phase transition. So before I get to that, let me give a space-time picture and put forward this question that, is this a classical transition or a quantum phase transition? Now, for people who are familiar with this, it's very almost trivial that how do you compute entanglement flowing through a circuit is very closely related to the idea of a minimal cut, which basically means that what is the minimum number of links in this space-time graph that you need to cut to break the circuit apart. And that's essentially, from a statistical mechanics point of view, that's understood as the entanglement membrane tension. You can really think of this as some sort of a membrane that you need to pull around and minimize the membrane tension in this. Now, we'll call this membrane tension S0 of R because this is very closely related to the 0th Renyi entropy as well. Now, if you have very sort of low measurement rate, then you can imagine that you actually have to cut an extensive number of links to disconnect the circuit. So you have a finite tension and you have an extensive operator entanglement. On the other hand, you can have a classical phase transition where your rate of measurements is so high that you actually have classically or geometrically disconnected the initial and the final times of the circuit. So what that means is because there is no cost to cutting a bond, which has been measured because it's already broken, at some measurement rate larger than this RC classical, you can always find a path through the circuit so that you basically can cut the circuit apart into two without actually paying any cost. So naturally here, the operator entanglement is 0, but this is really just a classical percolation transition determined on a graph, which is determined by the circuit geometry. So now the question we want to ask is there a bona fide quantum phase transition which is distinct from this classical phase transition, such that you have this regime where the circuit is classically connected but quantum disentangled? And what we hope is that we'll find something where the 0th entropy goes to 0 at some classical phase transition value, and the operator entanglement entropy for any arbitrary n not equal to 0 goes to 0 at this quantum phase transition. Now, this is the question we sort of, or this is the picture we want to formalize, which we did in this work. We sort of used 4 different prongs of this problem. So one is we solved the classical minimal cut problem. Then we actually mapped this problem onto an entanglement transition on quantum trees or tree tensor networks. And then, of course, we verified our results with exact simulations. And finally, we sort of proposed some speculative field theories for the phase transition, which is still very speculative. Now, in this talk, I'm only going to talk about these 2 parts of the work. Okay, so before I go into the sort of detail, let me specify the exact model for concreteness. So here is your all-to-all connected model. Each sort of block here represents a 4x4 Haar random unitary, which appears with a rate 1 minus R. And these broken lines with stars denote measurements. Now you can have true measurements where you say that you project a spin onto up or down with the bond rule probabilities. This leads to non-trivial correlated outcome probabilities. Or you can simplify your life further and say that, well, I'm going to do what is called a force measurement, where no matter what, I'm always going to project the spin onto its up state. And this is basically tantamount to doing post-selection in an experimental setup. Okay, so let's talk about the classical minimal cut problem very briefly. So the idea is that you can take this space-time graph and you can map every unitary onto a node. So for example, here I have mapped this circuit onto a node, onto a graph where I've color-coded the nodes. And then you can see that every node is connected to several other nodes just because of the world lines of the spins, and which give you the sort of links on this graph. Now, many of these links are missing or broken because of the measurement. For example, there could have been a link between these blue and green nodes, but which is missing because it was measured. Now, this is actually a very large graph because the sort of number of nodes is proportional to the system size and proportional to the time until which you run this circuit. On the other hand, it has a connectivity, or the maximum connectivity a node can have is only 4. So naturally, this means that this is a random sparse graph. And hence, you can sort of almost prove that loops are only going to be extremely large, and there aren't going to be any short loops. So you can organize this graph like a tree. You pick any node as your reference node, and then organize every other node according to the distance. And then you see that it's indeed a tree, but with sort of variable connectivity. Now, it's also useful to I was talking about measurement rates R, but it's also useful to define this quantity P, which is the probability that a site is measured before any unitary acts on it. So this is also sort of the probability of measurements. Okay, now once you have this probability, it's very easy to get the classical transition, because you know that for this tree to survive forever, because each node is branching into 3 or at best 3 links, you basically want 3 times 1 minus b to be larger than 1, and then that gives you a precise value of the classical phase transition point. What about scaling? So actually, what we do is we take these to solve this percolation problem, we take these graphs in terms of a layered Erdős-Renyi graph. So it's a random graph at a particular time slice. Then there's another time slice to which the links go up, and then so on and so forth. So that gives you a layered heterostratigraphic graph, and then you can do an effective continuum theory for percolation on such graphs. And that gives you a critical scaling of with a power law critical scaling with an exponent of 5/2. But just to make sure that this is not an artifact of the approximation we make, we actually simulate the classical limit of the circuit, and we indeed find that this power law exponent works quite well. So that sort of gives us a part of our phase diagram, that there is this classical phase transition at RC of 0.8. There's a power law scaling with an exponent of 5/2, and we have these two regimes, where deep inside this regime, you have a classically disconnected and obviously quantum disentangled tree. Deep inside this regime, you have a classically connected and a quantum entangled tree. And let's now go looking for this classically connected but quantum disentangled tree and hope that we find this quantum phase transition. So for that, we are going to study entanglement transitions on quantum trees. And the way I'd like to do it is, suppose I have this tree, and remember that there is in principle another bond sticking out of it. So you can take this tree tensor network and write it as an operator or a singular value decomposed operator in this form. Now, obviously there are only two singular values because these are qubits, and the top link has only sort of 2 degrees of freedom. And you can ask that, or you can basically state that the quantum information flowing between the base of the tree and the apex is quantified by the operator entanglement entropy of this particular operator. So let's sort of write it slightly formally, because this has only 2 singular normalized singular values, call them the larger one lambda max, the minimum, the smaller one lambda min. And you know that if I sort of write down the lambda min for a tree with k generations as zk, then this is the expression for the Renyi entropy between the apex and the base, and this is what we are going to compute. Now, I wrote down this tree tensor network, so let's actually look at the structure of the node tensor in some more detail. So each node tensor, you can see that has 1 link which comes out and 3 links which sort of go in. Now, the way it comes about is each node tensor, remember, comes from a unitary in your space-time graph. Now, as I sort of bent the links around to get a tree, what I did was essentially, I took one of the links that was going up and bent it down. So that sort of gives me the 3 input links to this tensor, and I get 1 node out. And on this sort of exit node, I put the measurement operator with probability p, or I just leave it as it is with probability 1 minus p. So that's the structure of my node tensor, and that sort of defines the ensemble of tree tensor networks that I'm going to study. Okay. Now, if I actually do forced measurements, where I project the spin only up and I have hard random unitaries, then it's very easy to show that these node tensors are statistically invariant under arbitrary U2 rotations of any of the indices. You don't have to actually sort of work it out in real time, it can be proven. And what that means is that the singular vectors, as I sort of grow my tree, are not correlated, and I only need to keep track of the singular vectors because, I need to keep track only of the singular values because that's enough to compute the Renyi entropy. So the way this is a very sort of useful simplification is because now I can compute things recursively. So the way I would do it is I'll take 3 trees with k generations. So these are my 3 trees with the colored as blue, orange, and green. I'm going to stick these trees to the input links of my hard random unitary. And then on the exit node, I'm going to put the measurement. And this is a tree with k plus 1 generations. And I can write down the minimum singular value of the tree with k plus 1 generations in terms of a nonlinear recursion relation, which takes in the 3 singular values from the k generations. This happens with probability 1 minus p. It's 0 with probability p, because if I measure, then obviously the minimum singular value is 0. Now, near phase transition, the Renyi entropy is going to be very small, and it turns out to be linearly proportional to zk or zk plus 1. So you can approximate zk plus 1 to be extremely small, and you can also study a linearized recursion relation. Now, the interesting thing is that this, the sort of specificity or the specific terms of this recursion relation, the nonlinear one or the linear one, depend only on the matrix elements of this hard random unitary. And we actually know a lot about how to average hard random unitaries, which makes the problem analytically tractable. Now, But even if you go outside this realms of exact, if you, in some cases you may not be able to exactly average, where what you can do is use something called a pool method. People who work in localization are very familiar with this, in something called the cavity method for computing Green's functions and trees and so on. But the essential idea is that you actually don't need to solve this exponentially large problem. You can do it in polynomial time. And the way you do it is you generate a large pool of zk to mimic the probability distribution of the singular values at the kth generation. Then you randomly select 3 members of them, plug it into this recursion relation, and you generate a member of the pool for the next generation. You repeat it several times, you actually get a distribution of the singular values for 1 generation higher. Now, this actually...
you have about 3 minutes. And
excellent. Okay. I think
plus 5 minutes of questions.
Okay, great. Okay, so what happens to this recursion relation? Now, if I actually solve the linear recursion relation, what I find is that if my measurement rate is very low, I mean the entangled phase, this actually runs off to positive infinity, or the distribution of log zk runs off to positive infinity. I'll come back to this point in a minute, but if I'm above the critical measurement rate, the distribution of log zk runs off to minus infinity, which means zk goes to 0, which is what the signature of the disentangled phase is. Now you can say that, well, how can this log zk run off to positive infinity? Because it's a normalized singular value. The reason it's doing this is it's the linear recursion relation. If I actually simulate or solve the nonlinear recursion relation, what the nonlinearity does is it leaves the disentangled phase untouched. But in the entangled phase, the nonlinearity acts as like a wall against which this distribution gets pushed, such that at infinite times, the distribution is restricted to order 1 values, and this is how the entangled phase comes about. Now, without getting into the details, basically this linear recursion relation is related to a traveling wave equation that Derrida and Spohn solved for in the context of directed polymers in random media, and then people have used this to study localization problems on trees. And you can sort of consider, okay, if I go back to this, you can easily see that the critical point is the one where the velocity of this traveling wave is actually equal to 0. So you can solve for all of that. And since you can compute the averages analytically for the Haar ensemble, you get an exact critical point, which importantly is distinct from the classical critical point. And if you actually add the nonlinearity, then the traveling wave problem maps onto a variant of another well-known nonlinear differential equation called the Fisher-KPP equation. And that actually gives you this very rapid exponential scaling near the critical point for the entanglement or the Rayleigh entanglement entropy. So that actually completes our phase diagram. So we have this classical phase transition, which is basically a percolation transition in my space-time graph that has a critical exponent of 5 halves. But the quantum phase transition for this particular model is very close to the classical phase transition, but it's distinct. And it actually has a completely different, very rapid scaling. So you indeed have this regime where the tree or the circuit is classically connected, but quantum disentangled. So with that, actually, let me just summarize. So I started off trying to understand the dynamics of entanglement in circuits which have unitaries and measurements. And essentially, we found that there can be an entanglement phase transition, which basically can be mapped onto entanglement transitions in quantum trees for this all-to-all circuits. And we found that there are there is a genuine bona fide quantum phase transition distinct from a classical phase transition, which actually has this very rapid scaling with this exponential form. And then, there are other sort of checks and processes you can do to make sure that it's indeed the case with microscopic simulations and so on, which I can discuss later on. So with that, let me thank you for your attention. Happy to take questions.
Thank you, Sthitadhi. We have about 4 minutes for questions. Before I go to Arnav, there is a question on chat by Prasanna Venkatesh Balasubramanian. Prasanna, do you want to unmute yourself and ask the question?
Yeah, sure. Hi, Shubhu. So just a quick question. So I should have asked at the beginning. So these measurements are they selective or are they non-selective? And if they're non-selective, can you in the sort of sufficiently large rate, think of this evolution as some kind of Lindblad or Krauss operator evolution?
Okay, so sorry, what do you mean selective?
Selective as in if you throw away the results. So if you can represent a measurement as just as in, yeah.
Yeah, okay, no, I understand. Yes, so you can definitely think of it in terms of a Lindblad. But then what happens is, of course, any measurement process can, with an appropriate time continuum limit, can be written down as a Lindblad. But that's actually not useful for me here, because once I do that, I'll get into a mixed state, right? So, and for the mixed state, then I need to get into the complications of how to actually compute the entanglement, because then I have to compute negativity and things like that, which, I mean, you can't compute fundamental entropy or any entropy for a mixed density matrix, because you have to distill out the classical entropy. Nevertheless, if you give me a Lindblad equation, what I can say is that, fine, I'm not going to look at the density matrix. I'm going to follow individual trajectories. I'm going to unravel my Lindblad. And so people have actually done that as well. And you do see a transition there in individual trajectories, not in the average density matrix.
Okay, thanks.
Arnav?
Yeah, Sthitadhi, so you showed these calculations for an all-to-all interaction. So could you just briefly tell me what is known if you have like a short-range Hamiltonian? Do these transitions survive, and what sort of things are known?
Okay, so the transitions definitely survive. Now, there is some debate on the exact nature of the transition. It might happen that this exponential scaling might not be there, and the phase transition might look a more conventional phase transition with a power law exponent. With a power law and with some finite exponent. That is, I think, the state of the art right now. So there is no sort of exact solution for the 1+1D circuit or 2+1D. So, but the phase transition definitely is there. And people like Andreas Ludwig and Roman Wasser and company, they have actually written down they have proposed conformal field theories for the critical point. So I think the very nature of the critical point is sort of, I would say, or how does the entanglement entropy go to zero as you come from the entangled phase is not very clear. But I think there are more or less very detailed proposals now on what exactly might the conformal field theory look like at the phase transition, even for 1+1D type models.
I see. Okay, thanks.
Yeah. But the transition is definitely there, even for 1+1D.
So, Victor?
Yes. So, is it in any way related to the Zeno effect or anti-Zeno effect as you increase the rate of measurements?
So I mean, yes. So if your measurement rate is so high that you sort of keep projecting the system onto the same state over and over again, then of course it's going to be in a disentangled phase. Now, then you can sort of keep refining the question and say that if I have a more complicated measurement setting where you sort of allow for some dynamics within the Zeno subspace, yes. But in this case, because I was sort of considering only very simple projective measurements, the Zeno phase would be sort of the boring phase where you project on some trivial complete zero entanglement product state.
Okay. Okay, thanks. Just one related. So there is also the anti-Zeno effect where instead of actually the dynamics slowing down, it accelerates. So did you see anything like that, or?
No, to be honest, I didn't, and I'm not very well versed with the anti-Zeno effect. So.
Okay, Christian Duda?
Yeah, Sthitadhi, just one quick question regarding that conformal field theory at the critical point. Do you know what's the nature of these theories? Are this the standard C type of theories, or is there something different about them?
As far as I understand, the theories are the standard C type conformal field theories, but there are multiple proposals. So I should. So
maybe I should look up the literature actually.
Yeah, I think
Yeah. Okay. Thanks.
I mean, we also tried not to do a conformal field theory. We sort of tried to do a Landau theory for this phase transition.
Okay.
But it, I mean, I can tell you in details about, there's a difficulty in taking because you need to have several copies of the circuit to compute these entropies. And then, when you try to average, you do the standard replica trick. But then as you take the limit of the number of replicas going to 0 or 1, you run into all sorts of problems. So that's where we got stuck. But I can tell you about that.
Yeah, that would be nice. Okay. Thanks.
Mona Lisa, very quickly.
Just a very general kind of question. You mentioned that you were interested in random circuits because they can be simulated on quantum chips or something. So is there also a Hamiltonian analog of this? I don't know, with cold atoms or something. So people do these kind of things.
Cold atoms, I don't know, because I think.
Sorry, Sthitadhi. While you answer the question, can you unshare your screen so that you can ask Nisheeta to share and be ready by the time you are done?
Right. So I'm not entirely sure how if you can do it on cold atoms, but you can definitely have a Hamiltonian analog of that, and people have studied measurement phase transitions in systems which are governed by Hamiltonian dynamics and are under continuous monitoring. Now, whether they can be done on cold atoms is not something I know, but theoretically you can study analogs of this with Hamiltonians and continuous measurements.
And you can't comment whether you expect the both quantum and classical kinds of transition there as well. So,
no. So of course, I mean, even within random circuits, there is a notion of Brownian quantum circuit. So, but I wouldn't exactly know how to define the percolation problem there, because I mean, of course, eventually, I have a percolation problem.
Sorry, Sthitadhi, very sorry, I have to intervene. We are
absolutely, yeah, I understand.
Quite late, and maybe you can join in the breakout rooms and discuss both you and Mona Lisa.
Sure.
Okay, sorry about that. But okay, can we move to the next talk? That's by Nisheeta. Nisheeta Desai from TIFR, and Nisheeta would be talking about duality. Sorry, Nisheeta, would you share your full screen? Now it's not full screen anymore.
Yes. Sorry, I had to unmute, so it wasn't unmuted.
Okay, yeah. Okay, so Nisheeta would be talking about duality and domain wall dynamics in twisted Kitaev chain, and this is a 13-minute talk. Nisheeta, I'll warn you at 11 minutes. Okay.
Thank you. I'd like to thank all the organizers for letting me present my work here. So I'm going to present this publication, this recent publication titled Duality and Domain Wall Dynamics in a Twisted Kitaev Chain. And so I was involved in the theory and simulations along with my PhD advisor at the University of Kentucky. So we were mainly concerned with explaining some terahertz spectroscopy data from the group of Peter Armitage at Johns Hopkins University. And I'm also going to share some more experimental data, some spectroscopy data that was provided by this group in Estonia. And I would also like to thank our crystal growers. So I'm going to start by talking about a very well-known model, the one-dimensional transverse field Ising model. So it's the simplest model that exhibits a quantum phase transition. So at low transverse fields, we have a ferromagnetic phase. There's twofold degeneracy. And as I increase the transverse field, I have a second order transition into a quantum paramagnetic phase where all the spins point along the transverse field. So with this being a very well-known model, you can ask, is there a material realization of this model, right? So turns out that in this quasi one-dimensional ferromagnet cobalt niobate, so it's a set of ferromagnetic chains. It was shown that a phase transition in the universality class of the Ising model was experimentally shown to be realized in this material by Koldia et al. In 2010. But even though close to the critical point, it's very close to the Ising model, far from the critical point, it's far from an ideal realization of the Ising model. So what are the things that make it different from the Ising model? So in the Ising model, in the ferromagnetic phase, the elementary excitations are domain walls. So this is a domain wall that separates all down spins from all up spins. And now if I apply a transverse field, that is a field transverse to the polarization, it causes the domain walls to hop. So in any experiment, you have local probes. So because you have local probes, you can always create an even number of domain walls. So with a local probe, there's no way of changing the parity of domain walls. So if you can always create 2 domain walls at a time, how does the dispersion of these domain walls look? So in experiments, most of the dispersion that you can see in experiments is dominated by 2 domain wall physics. So here I have shown some calculation, an approximate calculation of the dispersion in the transverse field Ising model. So the solid black line here is the dispersion from a single domain wall. So that is a standard hopping dispersion. And this is how it evolves when I increase the transverse field. And from here, I can calculate, assuming the domain walls are dilute and not interacting. From here, I can get an approximate dispersion for two domain walls. So it gives us a continuum, and the width of the continuum monotonically increases as I increase the transverse field. And you can see the gap, the energy gap also decreases as I increase the transverse field. So this kind of a continuum has been seen in neutron scattering experiments of Koldia. I mentioned this experiment before. So here they have applied some transverse field, and you can see that there is a continuum. So what cannot be explained by the Ising model is that even in the absence of an external transverse field, there is some bandwidth to the continuum. So you can see there's a continuum at 5 Kelvin, and as we reduce the temperature, the continuum splits into discrete spectrum, and that's because there are neighboring magnetically ordered chains that provide a Weiss field. But the question is, why is there still a bandwidth in the absence of a transverse field? What is it that causes the domain walls to hop in the absence of an external transverse field? So there has been previous work that tried to explain the neutron scattering data. So this is work by Sumiran, and they proposed a model with, you can see there are a number of interactions here apart from just the Ising exchange. And using this model that has, I guess, 3 tuning parameters, they were able to explain the neutron scattering data decently. So what we are trying to explain is some terahertz spectroscopy data. So in terahertz spectroscopy, you can only measure zero momentum excitations. So here you can see at 3 Kelvin, that's at a high temperature, there's a continuum. And as I go down to lower temperatures, the continuum splits into discrete peaks. So these are the excitations at zero momentum. And now how do these excitations vary as I apply a transverse field? So this is what was measured in the terahertz spectroscopy data. So on the left, I have the experimental data. So you can see that this has some very interesting features. The energy spectrum splits into 3 parts. So there's one part on the top that just keeps increasing with the energy, with the transverse field. There's one part that does not increase, the middle part does not change much. And then there's the low energy feature that sort of is broad in the beginning, then it narrows, and then it becomes broad again. So what can explain all of these? When you look at the transverse field Ising model data at zero momentum, you see the gap just monotonically decreases, while here the gap increases and then decreases, and this bandwidth just keeps on increasing. So what is it that can explain this? So let's look at the crystal structure of cobalt niobate. So this material has edge-sharing octahedra of oxygen atoms. So as you can see here, and the cobalt atoms are in the middle of these octahedra, and they form a zigzag chain. So inspired by previous work where they argued that in such a high symmetry crystal structure where you have edge-sharing octahedra, the cobalt ions are pseudo-spin halves, and they interact with Ising interactions, but the axis of the Ising interaction is bond dependent. So as you can see here, there is translational symmetry along the C direction, which connects next nearest neighbor atoms. So inspired by the crystal structure and these studies, we propose a new model, which we call the twisted Kitaev chain. So here you have Ising Ising interaction between nearest neighbor sites, but the axis of the Ising interaction alternates between 2 directions, N1 hat and N2 hat. So there's some angle 2 theta between N1 hat and N2 hat. So when theta is 0, it's the Ising model. When theta is 45 degrees, it's the Kitaev model. And when theta is less than 45 degrees, the ground state is a ferromagnet. And the polarization direction of the ferromagnet makes a compromise between the two directions N1 hat and N2 hat. So it bisects these two directions. So when I now write out this interaction in terms of polymatrices, so I call the direction of the polarization Z hat and the direction of the transverse field is X hat. Now, when I write it out in terms of polymatrices, it looks something like this. So now you can see here I have an interesting term where the sign of the term is oscillating between odd and even bonds because of this -1 to the I. So what is the effect of this term on the domain walls? How does it act on the domain wall subspace? That is the key to explaining the experimental data. So what it does is when you have a domain wall, it makes it hop with alternating amplitudes on odd and even bonds. So if on odd bonds, it's positive, the hopping amplitude is positive, on even bonds, it's negative. And so if you have a transverse field, then it has uniform hopping amplitudes. So in presence of a transverse field, you have alternating strong and weak amplitudes for the hopping on odd and even bonds. So this already reminds you of the Su, Schrieffer, Heeger model, where you have alternating hoppings. And so here I have shown on the left side is the dispersion of a single domain wall. And as I go to the right, I'm varying the transverse field, and I look at how the dispersion varies as I vary the transverse field. So now in any experiment, as I said, I always have at least 2 domain walls. I always have an even number of domain walls, right? So how do I derive now, how would the dispersion of 2 domain walls look given the dispersion of 1 domain wall? Now again, assuming these domain walls are dilute, these could occupy the bands in various ways. You could have 2 domain walls in the lowest band, or 2 in the upper band, or 1 in the upper band and 1 in the lower band. So depending on how they occupy these bands, the dispersion splits into three broad regions. And this is what we were seeing in the experiment as well. So this is a cartoon picture of what you would expect in the experiment. So given this qualitative description, how does the actual simulation of the twisted Kitaev model look? So we do a time-dependent DMRG simulation of our twisted Kitaev model. So this was done using the iTensor library. And so here I have shown 2 comparisons. One is above the critical temperature. So above the critical temperature is when all the chains are ferromagnetically ordered, but the individual chains have some incommensurate order. So there's no Weiss field.
Hi, Nisheeta.
Sorry. Yeah.
You have 2 minutes for the talk and then 2 minutes for questions.
Oh, okay. Thank you. So yes, so above the critical temperature where there's no Weiss field, there is still a continuum here, continuum of excitations. And as I reduce the temperatures or temperature, all the chains get magnetically ordered and create a Weiss field in the direction of the polarization. And that's what makes the continuum split into discrete energy levels. So here we used the angle theta as 17 degrees, and that's what gives a remarkable resemblance to the experiment. So this is one part of the experiment. And another thing that this was measured in a Fourier transform infrared spectroscopy, and what they were able to do experimentally show the signature of Kramer's Warnier duality. So there is a duality between the domain walls in the ferromagnetic phase and the spin flip excitations in the paramagnetic phase, and that's why the ferromagnetic gap closes at twice the rate as the paramagnetic phase, as the gap in the paramagnetic phase. Yeah, that shows the Kramer's Warnier duality between domain walls and spin flips. So to summarize, cobalt niobate is an excellent material realization of Ising criticality. But away from the critical point, it displays this rich domain wall physics that you can see in experiment. And we demonstrate that this is described by the bond-dependent interactions in twisted Kitaev model. Thank you. Thank you all for your attention.
Thank you, Nisheeta, for this nice talk. I think you unshared your slides,
Yes.
but in the meantime, questions from anyone? You can just raise your hand. And okay, let me start with one. Can you go back to your Hamiltonian that you wrote down with this bond dependent? So no, not this one. The next slide.
Okay. Yeah.
Okay.
Sorry, what is happening?
No, the next, yeah.
This one?
So this, yeah. So this -1 to the power I presumably can be gauged away by doing sublattice rotation about x-axis, right?
Yes. Yes.
So
right.
in this sort of new basis, I don't have a two-side unit cell. And so how do I understand this?
Yeah, so in the presence of a uniform transverse field, you can't do the gauge transformation.
Oh, I see.
Yes.
I see. Okay, thanks. The Arnav, do you want?
Yeah, so Nisheeta, quick question. So you showed this slide on this Kramers-Monnier duality. So, I mean, in the experiments, do you sort of see this in a, okay, so I mean, my question is, why do you see this duality over such a broad region, even though your microscopic is reasonably complicated? Is there some simple way to?
Right. So, yeah. So this is kind of yeah. So you do see it just after the 2 Tesla, right? And yeah. So it's if you go beyond the 2, if you go below 2 Tesla, you'll stop seeing it, as you can see right here. But yes, you do see it. So this twisted Kitaev model, it as you go closer and closer to the critical point, it starts behaving more and more like the Ising model. So yeah, that's yeah. I think that's the reason why it's the gap closing is in the same way as the Ising model.
Okay, maybe I'll think about it. Okay.
Yeah. Sorry, I wish I could answer that better.
Yeah. Okay.
Yeah.
Thanks.
Sorry, we are running a bit late, and let's thank Nisheeta once more for the nice talk, and we will move on to the last talk of the session by Samudra Sur from IISC. So Samudra, would you share your slide? Can you make it full screen?
Yeah. Okay, wait. Okay, so is the cursor visible?
Yes, the cursor is visible. Okay, so we will have the last talk of this session by Samudra Sur from IISc Bangalore, and he would be talking about driven Hubbard models on triangular lattice. And Samudra, I'll start your clock now. You would have 13 minutes, but at 11 minutes, I'll give you a warning. Okay?
All right. So let me begin by thanking the organizers. So I'll be talking about a driven Hubbard model on a triangular lattice, tunable Heisenberg antiferromagnet with 3 spin chiral term. So this work is done with my collaborator Aditi Udupa and my advisor Diptiman Sen. So as the name suggests, I have done some calculation on a periodically driven system. Such systems have Hamiltonians of this form, where Hamiltonian at time t is same as Hamiltonian at t plus the period. Now, since these are time-dependent Hamiltonians, there is no notion of energy eigenvalues or energy eigenstates. So these are described using Floquet theory, where one defines a Floquet operator, which is nothing but the time evolution operator over a period of drive. And then we analyze the Floquet states, which are the eigenstates of this Floquet operator, and the eigenvalues of the Floquet operator which are called Floquet. So this epsilon is known as the quasi-energy, and this is defined only modulo 2 pi over t. Okay, so we have done some calculation for a low energy effective Hamiltonian, but let me give an introduction. So time dependent many body quantum systems are often described by some effective low energy Hamiltonian. For example, half filled Hubbard model on spin half fermions in the large interaction limit reduces to a Heisenberg spin model. Now the question we ask is if we can derive a low energy effective model for a system which is driven periodically in time. And the answer is yes. So we use a technique called Floquet perturbation theory. But however, instead of energy, we have to say this is the quasi-energy effective model. So in our work, we derived a low energy Hamiltonian for periodically half-filled Hubbard model for electrons defined on a triangular lattice using Floquet perturbation theory. And we have analyzed the effective Hamiltonian using exact diagonalization and study its ground states. Okay, so we start with the Hubbard model with nearest neighbor hopping G and an on-site repulsion U. And this is driven periodically in time by the electric field of the form E1 cos omega t minus 2 E2 sin omega t. Now this E1 and E2 are along the same direction, but this direction makes an angle theta with the x-axis. Now the presence of both cosine omega t and sine twice omega t explicitly breaks the time reversal symmetry. Now this periodic drive can be added to the Hamiltonian as a phase to the hopping terms following Peierls prescription. So for a triangle with slides labeled 1, 2, and 3, the hoppings T12, T23, T31 become functions, obviously become functions of time, and on top of that they become functions of the frequency of the drive omega, A1, A2, which are the amplitudes of these cosine and sine fields, and the direction of the drive theta. Okay, so in Floquet perturbation theory, we just start by splitting the Hamiltonian into two parts, H0 and V, where H0 is the static part, which is the on-site Coulomb repulsion, and we take the time-dependent hopping portion as the perturbation. Now, for any state which satisfy time-dependent Schrodinger equation, we can have this expansion with time-dependent coefficient Cn, and then putting it in Schrodinger equation, we can have this equation for the Cn's. Now, under application of ut, psi 0 goes to psi t, and then plugging this equation back here, we can have this expression connecting C to C's at time t, which is connected by this ut operator. So the idea of Floquet perturbation is to solve this equation star iteratively to obtain an approximate expression for ut or an approximate expression of HF, which is known as the effective Hamiltonian, up to desired order in V. Okay, so we have done this calculation, and what we obtain is on a triangular lattice, we have this following effective Hamiltonian, which has this two spin Heisenberg interactions J alpha, J beta, and J gamma along these directions U, V, and W. So it's shown here. On top of that, we have a chiral 3-spin term given by this parameter C. And most interestingly, this sign of the chiral term flips for up and down pointing triangles. Okay. So this is something new that we have found in our system. Now the couplings J alpha, J beta, J gamma, and C are in general functions of the original Hubbard model, function of the parameters of the original Hubbard model, G and U, and also of the driving parameters A1, A2, omega, and theta, the direction of the field. Now, interestingly, as we said earlier, that the electric field breaks time reversal symmetry. If the electric field didn't break time reversal symmetry, these chiral terms would become 0. So we have our analytical expressions, which are not shown here, where it can be shown that if the electric field has time reversal symmetry, then the chiral term goes to 0. Okay, so now we have plotted some, for some values of the driving parameters, we have plotted the values of the parameters. So here we have shown in the 4 plots. So in the 4 plots, we have shown the values of J alpha, J beta, J gamma, and C as a function of the direction of the electric field theta. So we have kept the parameters G equals to 1, U equals to 20, which is much larger than G, omega equals to 17, and A1 equals to 35. And these 4 plots correspond to the different values of A2. So in all the 4 plots, we see the value of C, the 3-spin term, is always lesser than the 2-spin counterparts. But there are some plots where we show that the C can exceed the minimum of the 2-spin terms. Okay. Now these values give us an estimate of the possible values that these couplings can have. So with this knowledge, we have done an exact diagonalization study of this effective Hamiltonian on a 6x6 system. So the reason for choosing 6x6 lattice system is because we have used periodic boundary condition, and since it's a triangular lattice, there will be no frustration due to the periodic boundary condition imposed, and the number of spins are even, so that will allow us to work in the zero magnetization sector. Now the Hilbert space dimension for the 6x6 lattice is too large, which is 6.8 into 10 to the power 10. So we make use of these symmetries: zero magnetization, spin inversion, translations along X and Y direction. And also, in addition, if C equals to 0, we have the simultaneous parity inversion about X and Y direction. Then the Hilbert space dimension reduces significantly, 6.3 into 10 to the power 7, and this can be tractable in a computer. So 6x6 lattice size is the optimum size to analyze our ground state properties. So after calculating the ground states for various values of J alpha, J beta, J gamma, and C, we have calculated the static spin structure function in those ground states. So which is nothing but the Fourier transform of the 2-spin correlation function. And we find for all possible values of J alpha, J beta, J gamma, and C, which are practically achievable from periodic driving, we find a total of 7 types of static spin structure function plots. So of them, 4 correspond to the ordered phase, where the peaks occur in the Brillouin zone at certain points, and there are 3 static structure function plots corresponding to the disordered or spin liquid phases, where the peaks are over a broad region in the Brillouin zone. And one thing to note that our primitive lattice vectors are U and V, and that explains the shape of the Brillouin zone like this. Okay. So now so one important thing is the values of C that are obtained from periodic driving were, as I said, less, and at some times it were even greater than the minimum of the 2-spin values, the 2-spin coupling values. But what we see is the presence of C does not alter the static spin structure function figures. So we have basically to construct the phase diagram of the system, which we have done by this structure function calculations. We have set C equals to 0 and plotted all possible phases in this phase diagram. So we have a total of 7 phases, and these colors, this maroon, dark green, violet, correspond to the stripe or the collinear phases. The corresponding classical analogs are shown here, and this yellow corresponds to a spiral phase or a coplanar phase. This is shown here. Now, interestingly, we find that the transition from one stripe phase to another stripe phase happens through a spin liquid phase. So there are 3 spin liquid phases, which are intermediate in between these stripe phases. Okay. So now these phase boundaries were obtained from static structure function calculations, and these have been verified with other methods such as, let's say, fidelity susceptibility. So fidelity susceptibility is a concept that is borrowed from quantum information, and this is so let's define fidelity. This is defined as the inner product of 2 ground states of Hamiltonians, which has slightly different parameters, say lambda and lambda plus delta lambda. Then fidelity susceptibility is basically defined as the negative of the second derivative of the log of the fidelity. Now we have taken 3 lines on the phase diagram A, B, and C. I think people can see it on the slide.
Samudra, you have 2 minutes to end your talk and plus 2 minutes of questions.
Okay, thanks. So along these 3 lines, so these 3 lines encompasses all the 7 phases. So along these 3 lines, we have calculated fidelity susceptibility. And the idea is whenever there is a phase transition, the fidelity susceptibility would peak. So along lines A and C, which starts from a stripe phase, goes into a spin liquid phase and comes back to a stripe phase. So for these lines A and C, we have peaks of fidelity susceptibility occurring exactly at the places where there's a phase boundary. So that confirms the phase boundaries calculated from static spin structure functions. On the other hand, along line B, there is this transition from stripe phase to spiral phase to a spin liquid phase. There basically, exactly at those phase boundaries, this fidelity susceptibility blows up. That can be seen from these high values. Another way we have characterized these phase boundaries are real space correlation. So the idea is for ordered phase, this 2-spin correlation function goes to a finite value for a 2D system in the large distance limit. And for a spin liquid phase, this goes to 0 quickly in the large distance limit. So for a 6x6 lattice site with periodic boundary condition, the largest distance possible occurs halfway in the lattice because there is a periodic boundary condition. And we have plotted the minimum value of the 2-spin correlation, which captures the correlation at the largest distance. And along lines A and C, we see there is a continuous transition to 0 in the spin liquid phase, and then again it rises up as it comes back to the stripe phase. So this is along lines A and C, these transitions are continuous. On the other hand, along line B, we have very discrete or sharp jumps in the real space minimum correlation at these points at the phase boundaries from stripe to spiral and spiral to the spin liquid phases. But these lines match with the phase boundaries calculated from structure functions and the fidelity susceptibility. But along line B or any line which contains the spiral phase, the phase transition involving spiral phase is a first order phase transition, while along lines A and C, this is a continuous phase transition. Okay, so this is the summary. So we have obtained a tunable spin model for a half-filled Hubbard model on a triangular lattice by driving it periodically in time. The spin model has different Heisenberg couplings along 3 different directions and a chiral 3-spin term which has opposite signs for up and down pointing triangles. This term becomes 0 if the field has time reversal symmetry. And the spin model has 7 different phases, 4 ordered and 3 disordered, and the phase boundaries are calculated using static spin structure function, fidelity susceptibility, and real space correlations. Thank you.
Thank you, Samudra. Very interesting results. So interesting that I sort of lost track of time. But questions?
Can I ask a quick question? So,
yeah, or no?
Yeah. So they are very nice results, but I have a very dumb confusion. So that is that when you were showing your spin-spin correlations, you were of course doing some ground state calculation, right?
Yes.
But as you said, this is a Fluke problem. So
yeah.
I mean, I'm just wondering. So in a Fluke problem, what is the meaning of a ground state? Of course, I understand that you have this effective Hamiltonian, and you see what I'm trying to ask you, right?
Yeah. So basically, the other Fluke bands are actually the repetitions after omega. So like, so we have the energies defined only up to 0 to omega, and after that there is another Fluke band, or like another. So it's outside this temporal Brillouin zone. So we are only considering states inside that Brillouin zone, but these energies are actually defined. Well, you can just add omega or any n times omega, and we'll have the same phase.
Okay, maybe. Anyway, I'll think about it. Thanks. Yeah.
Okay.
Krishnendra, you can
okay.
just
sure. Sorry, Samudra, very nice talk. So the thing is that, so one clarification. So this was done within first order Fluke perturbation theory.
No. So we have gone up to third order.
Oh, okay. So, third order. Okay, I see. Okay, and the other thing is that how low in frequency have you got into?
So the Floquet perturbation theory actually only involves. I mean, the only condition is this: the hopping term should be much less than u.
No. What I'm asking is that as you lower in frequency, do you see different phases? Because the third order term might allow for that in principle.
Oh, okay. So I haven't checked that. Maybe I should.
Okay.
Maybe I should study that.
Okay. Yeah. No more questions.
Yeah.
Okay. Samudra, are there any other questions? Okay, I'll ask you two quick questions. One is that, do you know if I put C equal to 0, what is the classical phase diagram for this model? And so you just have these three ordered phases, and then there is a direct first order transition. Is that the classical phase? Okay.
Yeah. So okay. Sorry. Okay. Continue, please.
Okay. So then the question is that, do you know anything else about the spin liquid? Like what is the entanglement, or what is the spectrum, whether these are gapped? Because there is some recent understanding of J1, J2, J3 type of models on a triangular lattice, which seems to suggest that you may have a chiral spin liquid in some region where the symmetry is time reversal symmetry is spontaneously broken. Instead, even at C equal to 0.
Okay, so the one paper I know of that has analyzed basically this model, not this model, but there the C term was having same sign in all the triangles. So one can show that if the sign of C is same in all the triangles, then that creates a frustration, and there you can have chiral spin liquids. On the other hand, here the signs of C are up and down for so plus and minus for up and down pointing triangles. And here one can show, let's say, if there is a sublattice symmetry of A, B, and C atoms in this triangular lattice, then if there is a spin configuration and let's say all the couplings J alpha, J beta, J gamma are equal, then you have that symmetry. And let's say you have some spin configuration where the energy is minimized for the up pointing triangle, then for such staggered C, this will also minimize the energy for the down pointing triangle. So there is no frustration that is created by C alone. Okay, and so maybe I should look into more literature to answer the other parts of the question. But here's the classical phase diagram that you were asking. So these were obtained by these actually are verified by linear spin wave theory, which we have done.
No, this diagram sounds fine to me. Okay, maybe we can talk later. But before you ask your question, I think Sharon wants to make an announcement on behalf of the organizers. Can we have that announcement? First, thank Samudra for the nice talk. Sharon, you can make the announcement, and then Sthitadhi, you can ask that question.
Actually, one thing I would like to clarify. So you asked about the spin liquid. So we had also studied the ground state and the first excited state. So what it seems is in the spin liquid regions, so we have 6x6 lattice system. So in the spin liquid region, we feel that it is gapless. I mean, in the thermodynamic limit, it will be gapless spin liquid. But that's the only thing that we can say from this.
Okay, maybe we should talk about that.
Yeah, we should. Yeah. I'd be happy to talk about it.
Sharon, would you make the announcement, and then Sthitadhi, you can ask the question?
Yes, thank you. So there are two announcements. One, please remember that there is a special talk today starting at 4:30 by Anita Wronski from IIP Publishing, and followed by an evening session starting at 5. Please remember that the Zoom links are different. They're posted on Slack, and they can also be accessed through the scheduled program on the website that has been circulated amongst you. So that is that. And in the interest of time, I would suggest that it is best to close the session because there's not much time till the next talk. But I'll leave that to the discretion of the chair. Thank you.
yeah, maybe we can just ask to this question and close the session. Sthitadhi, please go ahead.
Yeah, I was just wondering how robust are your results to the order of perturbation that you go to? And one way of checking that could be that you might actually take your exact unitary and do ED on that. Have you tried that? So instead of doing ED on the effective H, you can do a unitary on the flow K unitary.
Samudra, I think you are still muted.
Yeah, so we haven't done that. Maybe that I should look into, because I can't really say about the robustness of the phases. But we see that these phases stay. I mean, the phase boundaries don't change as we change the system size from, let's say, 4 cross 6, 6 cross 3.
No, not the system size, but the order of the perturbation. But okay, I mean, yeah.
Okay, can I make a comment about this very quickly?
Yeah, sure.
Yeah, Shubhra, sorry, just
please go ahead.
Yeah, so Sthitadhi, if they are doing this perturbation at reasonably high frequency, which I think they are, then the results are not going to change much. You know, because all higher order Fluke perturbation results in this kind of thing is going to go down as 1 over some omega power, and you know, qualitatively there should not be much of a change.
But the frequency should not be higher than the many body bandwidth of the finite system, right? Because then in the thermodynamic limit it won't survive.
No, it need not be. But see, the point is that as long as the frequency is a little less than U, but larger than other scales in the problem, then you should be fine.
But I thought that then you would have some pre-thermal and long time scale, but not necessarily a phase. But okay, yeah, I see your point.
We'll see.
Yeah. So actually, yeah. So the U has been taken to be about 20 times the hopping, and the frequency is about 17 times the hopping. So they are actually much bigger than the hopping. And also, this U and omega have been definitely deliberately taken to be not integer multiples of each other, so that you are not at resonance. So we have been careful to avoid resonances, because that will completely spoil this spin Hamiltonian. But yeah,
okay.
Yeah, sure.
Okay, thanks, Ditunda, for the comments. So I think this is a good place to end the session. Let's thank all the speakers for the nice talks, and we meet at 4:30 in a different session.
Yes.